All right, so I guess this is a clarification also in case people don't see the aren't here yet. In general, the homework, and I mentioned this in class, I guess, but I guess I did not put it on the syllabus, so this is my fault here. The homework should be due at the beginning of class. Remember, you have those late days, so it's fine. And even above and beyond that, since there was some confusion about this for today, you can hand it in by, if you want, midnight tonight. So that's the last possible time in the day today. And that's fine. But and for the future, homework will be due at least starting those late days count at the beginning of class. So that will be the official time. And I'll also in general try to get back the homework by the next class if it's Thursday, I'll try to get it back by the next Tuesday. One note though is actually that the next homework I want to include some. I don't want to make just another machine learning assignment. I want to include actually a fair amount of electric power systems. So I'm going to wait until Tuesday to have that be sent out, and then it'll be due the following Tuesday. For that week, then I'll have extra office hours on the Friday before it's due, and then extra again on the Monday as normal to have the extra office hours. But yeah, again, it'll be out next Tuesday, and it'll be due then 2 weeks from Tuesday. And we have plenty of actually kind of space at the end of the class. We were currently having the last assignment being like 2 weeks or 3 weeks before the end of class, so this will work out. This will work out actually a lot better. So anything else? Were there any? Well, I guess if there were questions in the homework, then please come to office hours or come see me afterwards. I think I talked with a lot of people in office hours, so that's good. But do come and chat if you have any questions. So this last lecture concluded our first unit, really, of the course, so one of 3 units on machine learning. And the next unit is going to be on electric power systems. We're talking about energy and electricity in particular in this course a lot, and so it really is necessary to talk about how power and electricity actually works. It's, again, the big idea was that machine learning is good for things when you don't really have a model of a system. Things like how much energy our users as a whole going to predict. Very hard to model that, but when you have things like, if I hook up this battery to this resistor, what's going to happen? Well, it would be silly to try to build those models from data when we have a lot of good physics information about how these things actually work. So this is going to be sort of a switch. I imagine a lot of people that have a background in this, maybe not in machine learning or vice versa, will find these 2 units sort of differingly hard or easy, but the level of detail is about the same in both of them. We don't get into sort of a ton of depth on a lot of elements of electric power systems. This is meant kind of as a broad introduction about the various issues that arise here, and meant as kind of a first step into understanding these things. Though in some things we do go into a fair amount of detail, like power flow analysis or power markets. Those we will cover in a fair amount of detail. So the broad outline of this unit is we're going to talk about first basic AC and DC circuits, then about things like transformers and generators and, a little bit transmission lines maybe, but generators, 3-phase power, real and reactive power we'll get to actually today. Then things like power flow analysis, optimal power flow, and then power markets. And that's kind of the broad outline of what was going to cover. And if you didn't know what those things are, don't worry, we'll cover them all in depth. Today, though, we're going to kind of give a basic introduction to really linear models for electricity. And actually, who here has taken a course in DC circuits? So just basic electricity before, out of everyone here? Okay. Okay, maybe like 2/3, half or so. What about AC circuits? More or less? A little bit less, maybe. Okay. Again, the math here is quite simple, but if you haven't seen it before, there are a lot of good books I can recommend on this. Here, there actually are much more introductory books that are a little easier to read than maybe the machine learning texts we were talking about. And the math really isn't too hard, actually. I think if you got through the machine learning optimization stuff, this will be fairly straightforward. All you have to do use complex numbers here is the only harder thing, I guess. Okay, so again, before we sort of jump right into the details of DC systems, let's just talk a little bit from a high picture again about what electricity really means in this country. And I showed you this graph before, and if you come to a lot of talks actually on these things, you've probably seen this little chart 1,000 times now. Everyone seems to put it up, and it's guess growing in popularity. They put it at the kickoff of the Energy Institute, they had it, and then also on our panel someone else had it. So these slides were prepared before all of that, but it's just a really popular figure. And the reason is that it really does a good job of showing exactly where energy in our country comes from. So here you have solar, nuclear, hydro, wind, geothermal, natural gas, coal, biomass, and petroleum. And then it shows kind of the paths they take to being used and where they're used for. So electricity, in some sense, isn't really an end use of energy, right? It's just sort of a form in which energy can be converted to before being used. So electricity kind of sits up here by itself in that some of these things, like for example, natural gas for heating, maybe could be used directly in industrial, commercial, and residential consumer by these consumers. But then there's also some portion that goes to make electricity. And then that is used also in different ways by residential, commercial, or industrial customers. And a big point that people often make in this graph is that at the very end, there are these two categories here of rejected energy and energy services. And so what this kind of boils down to, and just the numbers here, you probably can't see them, but rejected energy comes to 56, what are these quads? Yeah, so quadrillion BTUs is what these units are here, but that's kind of, this is actually units of energy then. But about 56, quadrillion BTUs, the unit isn't important, it's just the percentage is important, are rejected, meaning that they go to things like basically heating up the air, literally, and that when you make put coal in a generator to make electricity, you're going to release some heat there. And that's considered rejected energy because that's energy you're creating. Thermal energy is energy, but it's not really being used for anything. In fact, it's just we have to really spend a lot of work to get rid of it and to get it out of these big cooling towers. And then 41, so the ratio here is 41 to about 56. That's the energy that we actually, in some sense, use. We actually use directly to do things like turn on lights or run air conditioners or I guess in transportation, for example, that's the amount of energy that actually goes into making the car move as opposed to just heating up the general engine and such. So people point out the fact that this is actually a very big amount here of rejected energy versus energy services. And the same happens for electricity, right? If you look at the amount of electricity that actually is used, quote unquote, it is 12 quads versus 26 that are being rejected. And that underscores the fact that actually generating electricity is quite difficult in terms of getting the inherent energy, for example, in coal or natural gas. Converting that to electricity is not actually the simplest process. And there's a lot of loss in that process. And people are always trying to make that process more efficient as well. So there is a lot that can be done here. And one nice thing about electricity is that at least it has the potential to provide a lot of these services directly, right? So once we convert energy to electricity, we actually, things like electric motors, air conditioners, these things are actually quite efficient at using that electricity. And so really, our focus on electricity is twofold. A, it provides a path to kind of this sustainable energy, right, where we can generate electricity sustainably. And the other thing is that it does allow us to really have a lot of potential end uses of that electricity. So that's a rough motivation of why we care so much about electricity when there clearly are other sources of energy. And the third reason, as I mentioned before, is really just that we can get lots of data about electricity, where it's much harder to get data, for example, about second-by-second consumption of gas in homes across the country, as we'd have with electricity, or not second-by-second, but say even hour-by-hour, which is what you guys use on your problem sets. That's hard to get, for example, for gas. Electricity is nice in that we have a lot of data on these things. Okay, so actually, are there any sort of just general questions about this chart? You've probably seen it a lot of times. You might have some thoughts about it. If you do, happy to just chat about them. This is a good time to talk about those things. It's the beginning of a new unit. Yeah?
Is there a version of it that shows, like, for each source of energy coming in through, how much of that particular source is rejected versus used?
Yes, there is. Yeah, it doesn't show it up on this one, I guess, but yes, there is. And what you have to look at basically is, for transportation, how efficient are petroleum engines, for example. For electricity generation, how efficient are different sources of energy coming in. For most fossil fuels, they're in the same order of magnitude at least. It's not like one you get 90% of the energy, another one you get 20%. They're at least roughly equivalent. I'm actually not quite sure what the efficiency of the latest, for example, gas or coal generators are. I could look that up, but they're at least in the same order of magnitude. Renewables, in some sense, are much more efficient because you're kind of extracting, the electricity you have. There's no real finite resource that you're using up when you generate that. But on the other hand, by some other metrics, if you think about the total energy in the wind or the total energy that hits a patch of ground and sunlight, even very good renewable sources can be very inefficient under that metric. If you just take the total amount of power hitting the ground versus how much they actually produce, that can be quite inefficient. So each of these different sources has their own levels of efficiency, and they're often similar regardless of what the actual end use is. The one big exception being things like heating, which is much more efficient. For gas, for example, it's much more efficient to burn gas for heat. If you want to use heat, then it would be, for example, to burn gas to make electricity and then use that to run an electric heater. That would be much, much less efficient than it would be to just burn the gas directly. There's another question, yeah.
Yeah, so the way that I'm reading this chart, the way you described it, it seems that transportation is actually extremely inefficient.
Yeah.
But that seems strange because I thought the internal combustion engine was actually a very effective way of using petroleum.
It's effective, but very inefficient on average. Because this is also averaged over. So actually, I forget exactly. There's something like 30 or 40% efficient at their maximum, or maybe even 50. Some really good ones at their maximum. Their optimal operating conditions. Engines, internal combustion engines are like 50% efficient at the absolute peak, and that might be even actually a pretty high number. It might be more like 40. But the problem here is that that's really taking into account the actual use of these things. So, for example, cars spend a lot of time idling. And that's very inefficient because you're getting nowhere and you're using some amount of energy still. So for the average use of petroleum for transportation, the ratio here is 7/21. So it's a third, a little less than a third actually, is actually being used. So that is the average efficiency of, a fourth, I mean. 25%. That actually is the average efficiency of petroleum in practice.
That's 100% efficient. I mean, maybe this is kind of a
so people,
right?
so could you make an engine that's 100% efficient? That would be really, really hard. And if you could, you'd be a really, really rich person very quickly. So you can
certain energy sources just have an inherently inefficient by this way of looking at it.
Yeah.
Using energy, and that's just intrinsically what it means to burn gas.
I think so. It does a little bit, just because the power inherent in a fossil fuel comes from the chemical energy, right? And the way we actually convert that to useful energy, be it electricity or moving, is to basically light it on fire and then use that heat to maybe expand things and push mechanical things that then turn and move. And there's a huge amount of heat that's released in this process that's very, very hard to recover. Essentially, you get energy from differences in heat, right? You get energy from the fact that some area is really hot and some area is not so hot, and that area that's really hot wants to push toward the area that's not very hot. And that's how you generate energy. It's extremely hard to extract all that in a way that would cool down that heat to the ambient temperature, right? That's going to be really, really hard to do. So these things it's not for lack of trying here. People try very hard, and they do make substantial progress. I mean, slow but steady progress in making these things more efficient. But there is this sort of inherent difficulty in directly converting chemical energy to mechanical energy. It is a very hard thing to do. Now, not batteries. Electricity, on the other hand, is quite a bit better. So electric motors are extremely efficient. But to generate that electricity, it's not that efficient if you're going to do it from fossil fuels, right? And the same goes for solar and wind. I mean, fundamentally, if you talk about the amount of energy there is in the wind or in a patch of ground, we're still not getting extracting all that much out of it. So making each of these things more efficient has the potential to drastically transform this landscape, but it's not nearly as simple as it might seem, right? It is not at all simple to design. We're just going to take all that inherent energy in a chemical and just turn it into some use. The one exception being for heating. Gas furnaces, for example, have gotten really, really close to 100% efficient in recent years. And so you can almost get out all that. If you ultimately want to heat things up, which is kind of the simplest thing to do, right? That is what the chemical energy releases when you burn it. Then it can actually be quite efficient. So, for example, heating homes with gas in terms of the actual efficiencies involved, is quite efficient. Now, whether it's still a fossil fuel, it still has these issues of carbon emissions, but it is an efficient use of the energy. So
is the story that we're supposed to draw from this graph then, like that other paths through the graph, like alternative ways of transforming energy might lead to less
right.
conflict?
So I think that's one of the things you can get from it is that we can still develop a lot of techniques that could potentially reduce this and increase this. That's one of the things you could think about. Another one is just getting an overall picture of what's going on here. And I think actually at the panel we had on Tuesday, Dave Anderson mentioned that what he takes away from this is the fact that there's no silver bullet that's going to fix energy as a whole, right? I mean, there are significant and different uses of energy throughout different sectors here. And it's not as if we could take one thing, even a major thing, like residential heating or something like that. Even if we get rid of that entirely, we're still using a lot of energy. So this is a complex problem, and there's no one thing that's, for example, taking up 90% of our energy that we could just make 100% more efficient. These are complex problems that will require attacks from many different angles. Electricity is nice as a way to attack that because we really can provide these services using electricity. And the one that isn't using electricity at all right now is transportation, but we could be, right? We can use electric cars. They actually are, from an efficiency standpoint, certainly if you ignore the battery, so we'll ignore the batteries for now, assume this is even just a fixed cost for the battery and there's no issues of sort of running out and things like that. In that case, they actually are quite a bit more efficient than generating energy from fossil fuels and running an electric engine. Because the generators here can be sized to the right scale, it actually can be much more efficient to just use that energy to generate electricity and then drive a car without electricity. Now you have issues of batteries and you have issues of the density of batteries and how long you can go, these kind of things. But from an efficiency standpoint, it's kind of a good story. A great summary of these issues is in that book I mentioned the first day of class, which is David Mackay's book on sustainable energy without the hot air, it's called. He really goes through these things from a very nice physical perspective and figures out kind of what things make sense in some ways and what things don't make sense. I think it's a really fantastic book. Okay, so this is fun. Okay, yeah. Great. More discussion.
For the rejected energy from electricity generation part, and I saw that when you conduct your electricity, wouldn't that depend on the requirement of the user?
Yes. So this is just sort of saying in fact, this is even it's estimated. So this is not directly measured, these things, but it's also for 2010. So for 1 year, this is how much energy we actually used in these different forms. So that year, we actually used this much electricity. That was due to the fact that people turned things on and off on their own accord. But this is just how much was actually needed, and so we had to generate that much.
So even though there's no single silver bullet, it seems like that 26 quadrillion BTUs, if we can maybe even harness half of that, that would still make a significant contribution.
You're thinking this one here, the rejected energy from electricity? Yeah, absolutely. So for example, one thing you can do, which has its own inefficiencies, so this is not going to harvest that much of it, but what's known as combined heat and power is a common thing that's at least pitched for this, in that the main waste product of this process here is heat, right? When you generate electricity at a plant, you generate a lot of heat. And so if we're also generating heat in homes and buildings, why don't we just pump that heat from the plants to the homes directly? Now, it turns out this is actually not that easy to do either, just pumping heat in this regard. And so the total efficiency in these cases is often not that much better than just building the most efficient plants possible and using the most efficient sources of heat. And there are some electric sources of heat actually that are quite good. So there are all these things that you can do, and it's actually great to think about these different ideas because they're all really kind of interesting. And how can we harness that heat better? What are we using heat for that we might be able to use that for? Heat is the main source of rejected energy here across all these things. So that's a great possibility, but it's also not, again, that if you figured out a way to use all of this or even half of this, you would be very, very rich. That would be, it'd be fantastic, but And by all means, you should be the ones thinking of ways to do this. This is going to be the future of energy. But it's not like it's a trivial thing. You can't just look at it and say, oh, look at all this waste. We'll do something useful with it. OK, so just looking at these numbers in a little more of a pie chart here. Let's look at just energy. Sorry, electricity here. So electricity now, this is just actually the inflows to this last graph here, though with different colors. But basically, almost half of it in the US comes from coal. This was in 2010. A good other portion comes from natural gas. This is actually projected to be on the rise due to cheaper availability of gas these days. A substantial but not very quickly growing fraction is generated from nuclear. There haven't been a lot of new nuclear plants built recently, and so this has kind of been a fixed quantity for a while, or at least not growing that rapidly. And then things like hydro, again, there aren't a lot of new dams going up, not that in the scale of, say, the Hoover Dam. We're not building many of those anymore. But there is a substantial portion here. And then things like wind, that should be solar, and geothermal, mainly wind in this pie chart, though, account for about 4%. And those are growing also very fast. So that was 4% now, but it's expanded hugely in the last 10 years or so. And I had, I think, the first day I had a graph of the growth in wind, and it really has grown from almost nothing maybe 15 years ago to, a small but still not zero portion of our electricity in the US here. And other is things like, actually, there's some use of oil still for electricity, though it's very little. You want to use oil in cars if you can. In terms of the consumption, again, it's actually kind of fairly evenly broken down between these sectors. I guess a little bit more in electricity, or a little bit more in residential and commercial buildings, which makes sense because those are places where you need air conditioning and you need lighting, and that's some of the big uses. And then also some in industrial, and very, very little in transportation, though. Despite the hopeful advent of electric cars, as of now, it's still a very small percentage actually used for transportation. So this hopefully gives you some sense of what electricity is doing in this country, right? What we're using it for and why we need it, too. Because this is actually, even though there are lots of other uses of energy here, this is actually, this is a substantial fraction of the total power here that's going into sort of funneled through electricity in its process to provide services for us. So electricity is a big piece of the pie, and it can be even bigger going forward. And again, it's one of the few that we really know how to produce in a sustainable way. Okay, so let's now take a step in more detail here and talk about electricity in, again, kind of the level you get basically in an introductory circuits course. Certainly today is not going to go past that at all. But if you haven't seen it before, it's very, very good to know some mathematical details and some physical details of what electricity is. So, starting from the very, very basics. A charge, which we're not going to talk about at all, but charge is kind of what electricity is in some sense. Charge, I'll take that back. Charge is the fundamental force behind electricity, I'll say. Charge is just, for purposes here, we're just going to say it's some property of matter that causes it to experience force when it's near other charges. Be those either similar charges, which will repel, or different charges which will attract. But it's just some property that makes things experience a force. And we typically measure that in coulombs, which are equal to the charge of 6.25 times 10 to the 18th protons. So the charge of a proton is think of as 1 in some sense. And but that's a tiny amount of actual charge. It's too tiny to even really talk about meaningfully. So we measure it in coulombs, which is a charge equal to some very, very big number of protons. And that can be either encapsulated in protons or in electrons, electrons being negative charge and protons being positive charge. Now, voltage, what voltage is voltage is the potential, is electric potential energy. What I mean by that is it's the potential to do work. Remember, energy in general was the ability to do work, which is move a force through a distance, and voltage is the potential to do this work, this kind of work. And it's measured in kind of a strange unit. We use the symbol little v or big V to denote it. It's also measured in volts. And it's kind of a strange unit. A volt is 1 joule per coulomb. So remember, a joule was our unit of energy that we had. And a volt then is just energy per unit charge. And the analogy everyone uses here, which quickly breaks down, is like water flowing through pipes, right? So charge is like some amount of water, and voltage would be like, for example, how high you raise that bit of water, right? So it's the same amount of water, but if you raise it to a higher height and then let it go, it has the ability to do more work because it has the ability to generate more force and do more work as it flows a longer distance down. And voltage is like that too. There's essentially, you can take the same amount of charge and kind of raise it to a higher potential energy by raising the voltage is what you're doing, and that is what voltage is. It's the amount of energy you can do per unit charge. Now, it's important to know that voltage really is a measure of difference in potential, electric potential. So you can never talk really about the volt, though people do informally. You in theory should never talk about the voltage at a particular point in, for example, electrical network, because you have to reference it to something. And so if you talk about that, it probably means you're referencing it to some zero voltage, which we call ground. We'll talk about that in a second. But basically, electric or voltage really measures a difference, right? Just like there's no absolute amount of energy, there's no absolute height where you'd want to raise water to give it some energy. What really matters is the height of water relative to some baseline, which you're going to let it drop to. And just like voltage, what really matters is the amount of potential that in one point relative to some other baseline, which you're going to essentially let it drop to or let it flow to, the electricity flow to. Again, that analogy of water breaks down quickly, especially when we talk about AC power, or AC circuits, because you talk about water flowing backward and forward all the time, and that just kind of gets a little bit silly. But it's a reasonable kind of analogy, at least to first thing, because things like current are also well captured by this analogy. So speaking of which, that's what voltage is. The other big thing, of course, is current, right? And current is flow of electrons or charge through a wire or through some material. In general, it's going to be a wire in our cases. Or I guess it actually be a resistor, and it could be all these things. But yeah, flow of charge through a material. Current is measured in amperes, and we use denote it with symbol I or I, which is actually going to be annoying because we've used I in the past to index over a bunch of integers. We have to use some different notation in different sections of this class. That's unfortunately just a little bit necessary. Hopefully everything will be clear from the context, but we're going to use I because it's the standard to talk about current. And what current is flow of this charge. So it's unit charge per second. So for example, in a wire, how many coulombs of energy are flowing to this point per second? That would be the current through that. Sorry, not coulombs of energy, God. How many coulombs of charge are flowing through this point in the wire? And unlike voltage, current then actually is only measured at a single point, right? Because what we want to ask is, at that point in the network, how much charge is flowing through that? And again, the analogy still works here. So what current is like in the water analogy is current is like the rate of flow of this water through, how much actual water is passing through a pipe per second. That would be the analogy for this. Remember, coulombs are like some amount of water, so current, therefore, is how much water is flowing through this pipe per second. And putting these two together, we remember that volts were joules per coulomb. Amps are coulombs per second. So if we want to talk about power, which is joules per second, or energy per unit time, we're gonna multiply together the voltage and the current. And that's, of course, the standard equation for power here. Power equals the current times the voltage. And the units, of course, cancel, right? Because a watt is 1 joule per second, which equals 1 volt times 1 ampere, which gives us this equation right here. Has anyone ever not seen any of this before? Okay, I should always ask that question because people are more hesitant to raise their hands, I guess, when I ask them if they have seen it. So, okay. All right, good. So now let's talk a little bit about DC or direct current circuits. DC circuits are essentially circuits where more or less current flows in one direction in the circuit, and it reaches a steady state flowing in just one direction. In these circuits, there are two kind of important sources, and these are voltage sources, which are by far the more common one that you'll see, and current sources. So a voltage source will maintain a fixed voltage drop, difference in potential voltage across the two ends. So this little symbol here, say 10 volts with a sign of positive and negative, means that there is a potential difference, a voltage difference across these 2 points here of 10 volts. Remember, voltage really is about 2 different points in the network, so we're saying here that these 2 points have a difference of 10 volts here. A current source, and actually that one's quite familiar because, for example, a battery is a reasonable approximation of a voltage source. It isn't exactly, and you'll see just how inexact it is if, for example, you were to hook up this as a closed circuit. Theoretically, there should be, therefore, kind of an infinite amount of current passing through this if there was zero resistance here, and a real battery will not do that. It will not produce an infinite amount of current for hooking it up. But for reasonable sized circuits and with enough resistors and everything to keep things reasonable, a battery acts somewhat like a voltage source. Now, the other kind of thing we might have is a current source, right? And that would just say that through this point in a network, there has to be a fixed amount of current flowing through that. And those are a little bit less common. We don't really see too many of those. It actually turns out that solar panels, or certain portions of solar panels, can be seen as current sources. So they will actually generate a current through a line and vary the voltage depending on how much actual, for example, sunlight's hitting it. Again, that's an approximation, but they can be modeled kind of similar to that. We just see a lot less of those in practice, so they're a lot less familiar to people, both current sources. And we won't really discuss many circuits with current sources here. It turns out when we talk about power on a grid level, neither of these are very good representations. It actually ends up being the case that we often directly produce power, which is the product of these two things, and the precise voltage. We can have a little bit of control over voltage maybe, but the precise voltage and current can actually vary a little bit depending on how that generator's running and how the loads are running. And the reason for this is that power is the actual amount of energy done per unit time. So for example, if you're cranking a big turbine to generate this energy, then sort of the actual work you're putting into the turbine directly reflects an energy you're generating here. So work per unit time would directly affect the power and the voltage in the generator. And the voltage and current may vary a little bit, but the power is really what you kind of have control over. So don't worry about that for now. We're going to talk about that actually in the next lecture, but just keep in mind that these are the kind of things you might see in DC circuits, but we're also going to see other types of sources in some sense going forward. A few more definitions here. I mentioned this earlier, but sometimes even though you always should talk about voltage difference at points in the network, it's sometimes very useful to talk about just voltage at a point. And when you say that, you usually want to relate it to some other point of voltage. And then a common thing is just to specify the ground here as being 0 voltage. And the name for that just comes from the fact that if you were to connect a wire to ground, the ground of the Earth is a very big sink. It can take up a whole lot of energy. And so that actually is a pretty reasonable approximation to something that will just basically fix a... You can't go low. Again, maybe the best analogy here is, again, that the water analogy. You really can't, in some sense, go lower than the ground when you're talking about water. And just like that with voltage, you can't get lower potential than the Earth. You can't do a lot with just the potential energy that is in the Earth itself. So we use that as a symbol there in our diagram. So actually, I should say I'm going to start drawing some circuit diagrams pretty soon with things like energy sources, voltage sources, and resistors, and other things, capacitors, and things like this. But these are the symbols that I'll use to draw those things in these graphs, or these diagrams. Okay, so in DC circuits, kind of one of the most important elements is the resistor. And the resistor, in some sense, just what it does is, as the name implies, it resists the flow of electricity. And resistance is going to be measured in ohms. And the unit of an ohm is 1 volt per 1 ampere. Now, that actual unit is probably much less important, the actual sort of physical significance of that unit, than just the fact that resistance is what relates current and voltage. And the way this works is by what's called Ohm's law. So this is talking about then a circuit where you have, for example, some fixed voltage, you have some resistance, and you want to find out the current. What you would do to compute that is you use Ohm's law. And this just says the voltage equals the current times the resistance. Again, show of hands, who has not seen Ohm's law before? Anyone? Who has seen it before? Okay. There's no one left out of that set, I think. Okay, great. So, and then you probably know that the symbol in circuit diagrams is this little line here, the little jagged line. Okay, so now we have things like this. We can put these all together and form little very simple circuits. So this is a circuit with a 5-volt potential difference. We're also looking at the negative side to ground. So we're going to assume this is, in some sense, 0. Everything here is going to have 0 voltage. And what happens here is that in this network, current will flow through these 2 resistors here. Now, the goal of what's called linear circuit analysis is essentially to look at circuits like this. This one's very, very easy, but you can get a lot more complex quickly. Look at circuits like this and determine what are the missing quantities from the known quantities. So in this case, for example, we know the voltage because we have a voltage source here that specifies these 2 points have a voltage potential difference of 5 volts. What we don't know initially here is, for example, the current. We don't know how much current is flowing through this thing. So every 2 points should have a voltage, every single point should have a current. And the goal of linear circuit analysis is to figure out what all those voltages and currents are, given the information that we know about the circuit. And it's called linear circuit analysis because these things, in general, you saw it in Ohm's law at first, right? Voltage is linearly related to current through this resistance here. But essentially, if you know the resistances, you know some of the currents maybe, and you know some of the voltages, you can, assuming you know enough of them, determine the missing held out ones. And in general, this takes the form of also called Ohm's law. But this Z will actually mean a few things later on in this course, but we'll call it for now the impedance matrix when it's all resistances. The vector form of Ohm's law is just that V equals Zi. Where here V is no longer just a single voltage. V is now actually a vector. V is a vector in Rn, so it's going to be the voltage at n different points in this graph. Now picking exactly which n points you should use is not always the most obvious thing, but there actually are very, very standard ways for doing this. Also, current is I is the current at n different points in this circuit here. Again, which points you pick depend on the actual structure of the circuit. And Z in general is going to be an n by n matrix. N by n. Got it. N by n matrix. So Ohm's law is kind of the simplest case of this, right? It's where all these things n equals 1, and all you have is just one thing that you care about. And then you just basically divide and multiply to get these things. In the general case, you have to use matrix operators to actually figure these things out. But it is actually still very, very simple. So there are a few rules you can use to kind of figure out exactly what these things might be in certain cases. So, for example, the 2 most well-known rules for resistances are about parallel and series circuits, so resistances in parallel and series. And the idea, which again is probably you guys have seen before, is that if you put two resistors in series, so you attach them one after the other, you can think of that as one resistor, where the total resistance equals the sum of these two resistances. Again, very simple, right? Because in some sense, the resistors have to be kind of like something physical that stops electricity, or resists the current. And so you'd think, of course, that putting two one after the other would do that twice as much. And that is what happens, in fact, if they're equal. Resistors in parallel operate by this other sort of well-known relationship here. So if you take two resistances and you attach them in parallel like this, well, intuitively, the resistance should actually go down, right? Because now you have more paths for electricity to actually flow, for current to flow here. You can go this way, and it can sort of go both these ways. So you actually should have less total resistance here. And that's captured by this, again, kind of pretty well-known relationship here, that in parallel, you take their inverses, and you add those, and you invert the whole thing, and that becomes the resistance of the parallel resistors. And the place this comes from, in some sense, is that hooking things up in parallel, what you're really doing is you're actually looking at kind of the inverse of resistance, right? Called conductance, but I even forget all those names. There's a million of them when we start getting into impedance and capacitance and all those kind of things. This inverse term actually adds, right? So I'll just say that I won't use C anymore because I forget that's not actually the usual term for it, but Ci equals 1 over Ri. Then the conductance of the total thing here would actually be just the sum of these two conductances. And if you want to then get back the resistance, you take 1 over this, right? R equals 1 over that, which equals 1 over this, which equals 1 over R1 plus 1 over R2. So that's where this comes from. But again, it's a pretty well-known law. You can just use it in practice. So that lets us do things like this, right? Now we can figure out, for example, we have this circuit here. And we want to know how much current is flowing through this wire. I have a whole bunch of resistances here. And the way we do that, we just kind of do it element by element. So here is a pair of resistors in parallel. So the resistance of that whole thing is going to be 1 over 1 half plus 1/4, which equals 4 over 3, right? We're going to add it to, I might make a mistake here, so please do correct me if I'm, it's pretty simple arithmetic, but yet when you're doing it in front of a big audience, you tend to make silly mistakes. So that then adds to 10, so we'll say that, so the R of so I guess R of, well, we'll call it, 2 and 3, and then R of the whole thing equals 10 plus this. So it would be 34 over 3. Then we use Ohm's law, which says the voltage equals the current times resistance. So current equals voltage over R here. And so it would be 5 over 34. So 15 over 34 would be the current here. So I1 equals 15 over 34. Now, these are pretty easy manipulations here. This is arithmetic that we're doing. But what if I gave you something a little more complicated? Sorry. Didn't mean to get to that yet. So this is actually pretty simple arithmetic. And in fact, there actually end up being two other laws that really you need to think about general circuits. This one's pretty easy. And in fact, these are kind of special cases of a more general law. And those two laws that really allow us to solve not just these ones, but any circuit which has whatever branches we want, any amount of resistors we want, sort of anything, those are called Kirchhoffs laws. So in particular, you've probably seen these before. There's two. There's Kirchhoffs Current Law and Kirchhoffs Voltage Law. And they each give you kind of a slightly different way of coming up for circuits with many different voltages and currents. They give you different ways of coming up with this Z matrix that lets you actually solve the system in this form. That's sort of what these two laws let you do, in addition to Ohm's law in the univariate sense. So what those are just the following. They're very intuitive, really. Kirchhoffs Voltage Law says that if we look at any closed loop in a circuit, right? So take any loop that makes a cycle like this, and we look at the voltage drop around this whole loop, around any elements in this whole loop, and we sum those all up, that has to equal 0. Again, sort of analogy, flow-wise in some sense, you can't have water. Actually, no, that's not a very good analogy. I take that back. What would be the better analogy for water? Anyway, I'll think of that one. The current one's easy, but the voltage one's actually a little can't quite think of it right now. Anyway, it makes sense, right? Because basically, if the voltage difference is going to be like this, some amount here, you need to somehow have the opposite of those things on the other sides of a loop. Otherwise, you would have a loop that essentially was somehow creating voltage in this loop of circuit, which doesn't make any sense. The second one is Kirchhoffs Current Law, and that says that the current flowing into and out of any node in the network has to sum to 0. And then that water analogy is very easy, right? Basically, you can't be creating more water just by a branch in your network that doesn't have any pump or anything. So in this case, if we have some node here where, just by convention, I'm going to say I1 is current flowing into this in this direction, and I2 and I3 are current flowing out of these two directions, then Kirchhoffs Current Law would say that I1 equals I2 plus I3, or I1 minus I2 minus I3 equals 0. If you write these all positive, so if you say all of these are actually kind of flowing into the network, then you would just write it as the sum of all these i's equals 0. And just with the convention that negative current then would mean there's actually current flowing out. Now, these are sort of simple. And it turns out that if you use these laws, what you can do is, along with Ohm's law, what you can do is write down this set of linear equations for any circuit, or any DC circuit. AC you can too, but they're a little bit different here. This set of equations, using just the voltages we know about, Kirchhoffs Current Law, Kirchhoffs Voltage Law, you can write down what Z has to be to solve this equation. Now, if you've taken a course on electricity, and probably a lot of you have a long time ago, you've probably learned a lot of ways of actually doing this, right? So say we get a circuit like this. You probably maybe even remember how to do this. It would take me a little while, actually. You would compute right equivalent circuits of this and do things like that, and write the expression of the Kirchhoffs voltage law or the current law, depending on this, like the mesh loop method and the mesh node method. But basically, you use these laws to write down a big expression for all this, and then you can solve it. And it basically is, it can get pretty tedious very quickly. Even something like this, right? This is a situation where you actually have, it's not like you just have one thing in series or in parallel anymore, right? I mean, how do you deal with this type of situation here? You have current can go kind of any of these ways around this whole network here. How do you use our, say, resistance laws to actually figure out what's happening here? And it's not that trivial, actually. Again, it's probably the first assignment you get for EE 101, but it's not something that just popped out at you immediately. The point I want to make is that just like with optimization, we're never going to actually do this in this class. We're never going to worry about this too much, because that's the thing about computation is there are all these programs that do this for you really, really easily. So we're going to use one, and I'll demo it a little bit now. There's probably the most famous of these is something known as SPICE. If you've ever seen that before, so SPICE is a big circuit simulator that does this. I mean, there's a lot, much more than that too. I'm going to use one for this class and use it for the homework. It's called QUUX, which stands for the Quite Universal Circuit Simulator. And actually, I wonder if you can see in the video. I'll try to stand over here, even if I'm out of the frame. And what you can do in this program is just actually lay out a circuit and just see what actually happens in the circuit. And so we can lay out that circuit without ever actually having to go through all that math of computing it. We can just see what actually happens. So let me just actually draw this. So here, I'll put a source, which is a voltage source. Plot that down. I'll fix all the numbers in a second because I don't actually remember what they are. In lumped components here, you can place resistors. So I'll put a bunch of resistors in. I'll fix those numbers in a second, but in this little network that I showed you in the past slide. Okay, I'll put a ground in, which sets a reference voltage for the network. And now I'll start drawing all the wires that connect everything together. And I'm doing this just bit by bit here, just so you can see that it actually is quite easy. You will do this in your homework, and you'll be using Quux here. So it's really a really nice tool. It lets you basically, I mean, I guess you have to actually go through the hassle of drawing all these lines. And it can depend on your sort of level of familiarity with these two laws, whether you think that's better or worse than, whoops, I want to delete this one. Whether you think it's better or worse than just doing what I did right there. For me, that's a whole lot easier. And especially when you talk about AC power and things like this, it can be much easier for me to sometimes just draw the network and simulate it and see what it does. So now, and I'm going through this in detail because you will do this on the homework. You'll experiment with these things, so it's good to know how to do it. Let me just actually get the exact resistances there. Anyone remember what all those were? So it's 1, 1, so it's 1, 1, 1, 2, 2, and 3, 3. So let's just set those up as the resistances and currents there. So here, 1 ohm. Whoops, 1. I don't know if you need the ohm there, actually. I don't know about that. 1 ohm there. Here, these were 2, right? This was 2. And then these were 3. Okay. What did I do?
R1.
R1 is 50. Oh, I didn't press return, I guess. Okay. The voltage was 5 volts that we had set to. 5 volts. Okay. So we set up our circuit now. Now, what we wanted to ask in that last slide, I believe, was what was the current that would flow through it? Just what was the current that went through this part right here? So to do that, and you can do it actually in a few ways, but the most sort of explicit way to do it is to build a probe here, and you select the current probe, and you just plop that down in your network like that. I hope, oops, let me, I think I dropped 2 by accident. Yeah, okay, that is connected, good. Okay, so now you just plop the current probe down, and you can actually do it. And this, I mean, if you've built a system, this is exactly what you do when you would build the system. You just have to actually go ahead and build it, right? You hook up a current probe there, and you look at those little stupid colors that everyone has. No, I shouldn't say stupid. You look at those little colors that denote the resistances, and you try to look up tables and see what they all are, and you find all these resistors here, and then you lay it all out on a breadboard, and you run it, and you get the answer. That's even more hard. That's much harder than even doing it with Kirchhoffs laws, but this is even easier for me, at least. So now the last thing you have to do is to simulate this. You need to drop a simulation block. And Quux actually lets you do a lot of different types of simulation. Like you can do DC simulation, you can do transient simulation, which actually lets you look at the transient power if you have things like switching voltage, switching regulators and these kind of things. But in our case, we're just going to drop, and we'll use that actually all to talk when we talk about a little bit about things like power electronics. We'll actually also use Quux to see, for example, how some DC-DC electronics can work. But here, don't worry about that if that didn't parse quite yet. We're just going to drop a DC simulation block, and I might have to save this actually. Okay, so I'll just save it. Whoops, I created a new one. Save it as circuit 3. Save, and now we press this little button that says simulate. So everything looked good here. And what we can do now is a little bit of a pain, but you'll get used to this whole process very quickly. We've simulated it now. Everything looks good. If I take something out, and I'll show that in a second, that will create an error and say something went funky, something isn't working here. But if everything looks good, you drop in your diagrams. You select diagrams here from the thing last. That was simulations. You select diagrams, and you can just drop a table of different values. And for example, one thing you can select is what is the actual current. So the current flowing through there is 1.88. And that's the same number you would have gotten, of course, had you gone through all the math. Nice thing here is we can just change things, right? We can just say, and I guess, you can do this too if you construct your matrices right, but you just do that, simulate it again, and what you get is you get a different number of what that current is, of course, because you changed the resistance there. If you, and I think this, no, that won't be enough to break it. Let's see, if I just delete this wire, for example, this should break it. Nope, it's happy just to say there's no current flowing through it, as there shouldn't be. Of course I wouldn't break it. Let's see, what would actually, in DC, I should forget what you can even do to break these things. I'm sure you'll discover on the homework what you can do to actually mess these things up very quickly. But essentially, what's nice about this is, again, as I said, you don't have to worry about, was there some question?
Want to know where the DC simulation.
Oh yeah. So DC simulations, you select it from this diagram, from this chart here, the simulations. You just take this block and you just put it in somewhere. That's all you do. That just lets you know that you're running a DC simulation versus, say, an AC simulation. So when we talk about AC power, we'll do the same thing, but we'll have to, an AC circuits, but we'll have to use the slightly different versions of this. So we'll drop the AC simulation block here. We'll also, I don't think any of the homework questions will involve it, but when I talk about power electronics, I'll use a transient simulation. The rest of these you don't have to worry about. They're for things like digital logic or to run experiments where you sweep over parameters or sweeping over frequency spaces, those kind of things. But we won't use those here. Okay, so this is sort of what's really nice about all this current software is that we can essentially ignore a lot of the mathematical issues that come up with writing out those equations by hand. Now, just like with optimization, it's probably good, if you're going to do this sort of in a lot of detail, it's good to know how these things work. It doesn't replace the fact of sort of knowing how to do it. But you can kind of also, like with optimization, just say, like we did there, we said, I'll say, YAML will figure out how to optimize this thing. You don't have to worry about it. Here we're going to say, OK, this thing will figure out how to compute Kirchhoffs laws in a way that will solve all these things, and we won't worry about it. Of course, what it's doing internally is it's solving Kirchhoffs laws. Or using Kirchhoffs laws to set up those equations. Internally, it's doing that. And in fact, for a specific type of network that we encounter in power systems, there are some very simple ways to build these networks that are kind of very easy. And then we will cover that. But we won't talk about how to do it in these kind of general networks here. OK, so that's the first demo you see of Quark. So use it a lot, and we'll use it actually a fair amount, both for AC power and DC power. So where did I put there we go. OK, so that was all I want to say about DC circuits. Oops, let me go full screen here. I have 20 minutes left. OK, so that's all I want to say about DC circuits. And the rest of the time, I still at least want to introduce the ideas related to AC circuits and AC power. Probably won't get to AC power today, but we'll get to AC circuits a little bit. So AC circuits, unlike DC, have current and voltage that actually oscillate continuously. So an AC voltage source, for example, would actually oscillate sinusoidally. And I guess it doesn't have to be sinusoidal to still be called AC, but all the AC we'll talk about here is always sinusoidal. Voltage sources are sinusoidal currents. Until we get to power electronics, then we'll talk about something a little bit different. But you can think of this as always being sinusoidal. The voltage, certainly, at least. And really, it's just this basic expression here is just saying that the voltage at time t equals, well, some maximum voltage times the sine of omega t. Omega then is the frequency of this oscillation plus phi, which is here some phase angle. So Vmax in this expression is the peak voltage, is how high it goes. This would be a peak voltage of 1. The frequency here is, I guess, actually typically scaled in use of radians. So you would include the radians in the frequency calculation, for example. So for example, if you wanted this thing to oscillate 60 times a second and your time was in seconds, then omega would be 60 times 2 pi. Right? Because every time you get 0 to 2 pi there, you go through one complete revolution cycle. Here I'm showing the axis of t divided by omega, so it actually goes a full cycle in 1 unit of scale time. And then phi here is the phase angle, which is essentially what's the offset from starting at 0 that we would have here. When you just have voltage source, just a voltage source on its own, the phase angle is somewhat arbitrary, right? It doesn't really matter what you say that is. But when we start talking about currents and voltages, then all of a sudden the phase angle becomes very important. The relative phase angle in particular becomes very important. Now there are two conventions for reporting the magnitude of these voltages, right? So for DC it's easy. You just look at what the voltage is and you report what the voltage is. That's the magnitude of the voltage. For AC, it's not quite as simple, because what do you actually report as being how much voltage is this? There are two conventions. One is just to report the peak voltage. So just if this is a max voltage of 1, that's Vmax is 1, so that has a magnitude of 1. That's actually not the most common at all. The much more common one is called root mean squared voltage. And what that is you take this thing, you square it, you take the integral of this thing squared over 1 cycle, you average that over the cycle itself, and you divide, or you take the square root of that whole thing. So what that would be is the integral of this middle term here, so it's sine squared times the voltage max squared. Integral from 0 to 2 pi, so that would be 1 cycle of the voltage. You divide by that size of the cycle there, and take the square root. And through some integrals, which we don't have to do, but which you can just look up, can you actually see that? Maybe. I was trying to be able to access my computer, but I might have actually inadvertently blocked some of the bottom of the slides. By some simple integral, this actually happens to be 1 over the square root of 2 times the maximum voltage. So just know, for example, that when people talk about AC voltage, they almost always talk about root mean squared voltage. For example, the outlets in rooms are 120 volts. What that really means is that the peak voltage is about 177 volts. And it's the root mean squared voltage that's about 120. Not exactly, actually. It can vary by a good amount in practice. But the number 120 for voltage in the US, that is root mean squared voltage. You know, I actually didn't see if there were any questions about DC circuits when I stopped that unit, and that probably would have been a good idea to take questions. So let me retroactively ask if there are any questions, either about this or about DC circuits. So we're all going through it kind of fast, but I presume most people have seen this before, so we'll just go through it fast. OK. So just like with DC circuits, you could have an AC voltage source. And this we denote as a little squiggly line like this. So there's the same kind of circle here and a little squiggly line here that lets you know this is an AC voltage source. And this just like a DC voltage source, this just maintains now a sinusoidal voltage at this precise, usually root mean squared voltage. It doesn't specify the frequency in a lot of these things. You could specify frequency too if you wanted on those things. Usually it's kind of implicit. You sort of know what frequency should be for these things, so you don't specify it, but you can too. For a lot of the analysis, actually, in steady state AC, the frequency doesn't matter if you just have resistance quantities. When you start having capacitors and inductors, then it does matter, the frequency. So knowing the frequency is important, but usually it's kind of implied or said elsewhere. And just like with DC, we can hook up an AC voltage source in a circuit like this and have that current happily flow this way a little bit and then that other way a little bit too. And for purely resistive circuits, this is actually very simple, right? Because all we have is we just have Ohm's law being applied at every single point in time. So the voltage at time t is just equal to the current at time t times the resistance. So it's no different from the DC case in some sense. And so, for example, in this case, if the voltage is, again, by convention Vmax, the sine of this thing times that, then lo and behold, the current is just the same thing with Vmax divided by R times this, because current then is just the voltage divided by R. And what the graph of that looks like is kind of boring, right? It's just saying that, okay, voltage is oscillating sinusoidally, and so is current. The important thing to know, though, is that these two things are oscillating with the same phase angle. So they are in phase, right? Whenever this is at its peak, so is that one. And this might seem kind of obvious here. Of course, all you have happening here is this Ohm's law, but we're shortly going to see that this actually changes for different elements in circuits. So what are these elements? The two elements we're going to talk about, and I think I have time to cover these because, again, I think people have seen most of this before, is inductors and capacitors. So those are the two other big elements that people talk about in linear circuits. These are all still linear circuits. What I mean by that is just we can express voltages and currents in this form still. Now, this might seem a little bit weird, right? Because we're saying, okay, voltage, we're going to call it a linear function of that, but things are sinusoidal, right? How is that at all linear? It will turn out that we can express these sinusoidal currents and voltages using complex numbers in a way that actually keeps everything still linear. Won't worry with that just quite yet. We'll probably get that the first bit next time. But basically, these types of expressions still hold when you have resistors, capacitors, and inductors. When you start adding other things like diodes or power electronics, this will no longer hold. And so those are non-linear circuits. But these here are linear circuits. They obey these laws. Linear laws like this. Every circuit obeys these laws too, but they keep everything linear. Okay, so an inductor is something that resists change in current. So if you have no current flowing through something, an inductor, and you want to put some current flowing through it, it will fight back against that, for a little while at least. Inductance is measured in henries. The unit of a henry is 1 second times 1 ohm. Again, that isn't that important. What's really important is this law right here. Inductors also, just like resistors, relate voltage and current. But they do it in terms of the derivative, the time derivative of the current. And the important law for the inductor is that voltage equals the inductance L times the derivative of the current, the time derivative of the current. Right, so what this means is that, for example, if voltage is fixed, if you hook up an inductor, and don't do this, by the way, but if you were to hook up an inductor to a fixed voltage source, I should probably use our notation that I'm using in class here. If you use a fixed voltage source and hook up an inductor, the sign for an inductor is little squiggly lines like this. That symbolizes actually a magnetic coil, and inductors are built with magnetic coils. So essentially you have a big coil of wire, and what happens is that the actual magnetic field created by this wire resists the change in current. So if you were to do this with a fixed voltage source here, say 5 volts, then what this is saying is that the derivative of current would increase linearly, right? The derivative of current would sort of be, so here's a graph then of current over time. If it started out at 0, it would actually be increasing because the derivative would be constant function of the voltage itself. So current would just keep going up linearly. Now this is not a good idea to do. Don't hook up a DC circuit to an inductor because it just eventually will become just like an open loop, right? An open bit of wire, and eventually you'll start burning things out. In AC circuits, it's okay to hook them up to an AC circuit because the voltage is always changing. These actually do not damage anything horribly. They're okay. But this is kind of the fundamental law, and we'll see how that plays out right now in AC circuits. So this is the fundamental law of inductors. This is their symbol. Their little coils of wire is the way to remember that symbol. And now what happens if we were to hook up an inductor to an AC voltage source? It's no longer the bad thing like we did with the DC's case. It wouldn't just increase forever. Something different happens. And the way we derive this is we just take our expressions for the inductor, and we just use a little bit of calculus. I think this is the only place we're actually going to use an integral. These few lectures, we use lots of derivatives in this class, but for some reason you don't use that many integrals. But anyway, here we're going to use an integral. So the derivative of respect to time of the current equals, or times the inductance equals the voltage. That's the fundamental law of the inductor. So to find out what the current is then, let's integrate this thing, right? So we can integrate this here. First we divide this side by L. We integrate this thing here. When you integrate a sine function, you get a cosine function, in fact a negative cosine function, plus you have to also get dividing it, the term is multiplying t here, so you get V max over L times the frequency times the cosine of this thing. And remember, cosines and sines are the same thing, they're just one's 90 degrees out of phase with the other. So you can convert this to a sine wave too, where it's the same thing as before, but you subtract off pi over 2 in the phase angle. Does everyone follow that derivation there? Sort of just very simple calculus using the fact that the integral of a sine is a cosine. And you can check it sometimes it's easier to check derivatives than it is to check integrals, but if you differentiate this, an omega would pop out there, they would cancel, and you'd get the sine term there, the omegas would cancel, and you'd have this original expression. Okay, so the important thing to note about this is that you have this term over here. So remember, for the resistor, IT just equals V max over R times the sine of omega t plus phi. That's all you have. The important thing about this case is that you get an extra term here. In the inductor case, you have the current equals V max over L, and also get an omega here. So in some sense, the size of the inductors you use, the order of magnitude you should think about, in some sense, if you're going to compare it to resistors, you also have to factor in the frequency. So that's important. So these are going to be different. So the inductance and the resistances will be, as their base units, kind of different orders of magnitude. And they can be very different orders of magnitude if you start talking about very high frequency circuits. For AC circuits, this is 60. And so in the US, AC voltage comes at 60 hertz. So omega is 60 times 2 pi. So these are on the order of 300 or so apart, L's and R's. But this depends on your precise frequency of your circuit as well. Didn't write that very clearly. Let me just write that a little bigger. But the other important part is that you still have the same term as before, T plus phi, but you have this other term, this lag. So you've not only changed the magnitude, the current there is not only a different magnitude, because you multiply it by this term, you also shift the phase of this current here. And in particular, this is the plot of these two things. And in this plot, the current lags behind the voltage by 90 degrees. Important to know that this figure, even though it looks like it's shifted that way, is lagging behind, right? Because when this is here, this is down here, and by the time this is up, this has come to 0. So current's kind of following behind voltage by 90 degrees. And that's exactly what this expression is saying here. So inductors cause the current to lag behind the voltage. The other element, and let me see if hopefully I'll have time to finish this. The other big element are capacitors. So capacitors are kind of like they're the counterpart of inductors, right? Capacitors, what they do in some sense is they store electric charge. Essentially we have 5 minutes before class ends. I'm not sure I'm going to get through all the same derivations before, so we'll pick up next time with capacitors. But just very, very briefly, I'll go for a few more minutes. Capacitors are kind of going to be a different analog of this. Capacitors, what they are physically is they're two plates. They can store charge. And they're separated by some very sort of thin material where charge cannot pass through. And what this does is when you hook up a capacitor to a battery, what would happen is that these two plates would store charge at first. So at first current would flow, and the plates would build up positive and negative charges. And then eventually they'd kind of be full. They couldn't build up any more charge, and so current would stop flowing. Capacitance is measured in farads. Use the symbol C to denote capacitance. Again, the technical definition is a farad is just 1 second per ohm. But what's really important about capacitance is this law, which is just sort of the reverse of what we saw for the inductance. Here, current equals the capacitance times the time derivative of voltage. That defines what a capacitor does. So if you could imagine having a fixed current source and a capacitor, so say you had a diagram like this. Also, I mean, there's hard to find current sources like this, but don't do this. Because in order to keep a fixed current flowing through that, right, according to this law, you would need to keep linearly increasing the voltage. So what you'd have is maybe the voltage drop here. So this is when I say voltage, I mean really the voltage drop here. So the voltage over time, starting out, if there's no charge, if there's no difference, it would just start increasing and go up forever, much like the current would with a inductor. Now, don't do this, but it's also hard to even find the source that will quite do this. Basically, it would just mean these things would have to keep, in order to maintain a current, you have to keep putting more and more charge into this thing, which would increase the voltage drop. And I'll explain in a second how this same equation results in something very similar to this, but instead of making the voltage angle, the current lag by 90 degrees, it will make the current actually lead voltage by 90 degrees in a capacitor. Okay, so again, I think probably most people have seen a lot of this before, but this is the basis for a lot of what we're going to do with electricity later on in this course. So it's good to kind of go over it again. But we'll pick up next time with finishing up capacitors and talking about AC power.